Okay, so welcome to the board, and I'm going to be talking about 5 applications slash problems that are in some cases relevant to the real world. In some cases they're more purely computer science-y problems, like something that you might find on a programming homework. Okay, they all involve discrete math. So we're going to talk about virus spreading, speed dating, online advertising. Look at the wide array of problems to which discrete math is relevant. Okay, and then I'll introduce you to a domino puzzle and a subset sum. These are going to be, related to the challenge problems that are worth money, so pay attention. Okay, so virus spreading. Now we have COVID, before we had Ebola. Every now and again viruses pop up. So imagine people are squares and they live on a grid. Okay. So I'm going to draw a 7x7 grid here. And I'm drawing slowly so you can draw with me. So draw. Take notes. Okay, 1, 2, 3, 4, 5, 6, 7. And it's going to be a 7x7 grid. 3, 4, 5, 6, 7. Okay, and the idea is that this you can think of a person as a white square, and let's say this is me. I have 4 neighbors: north, south, east, west. Okay. Now some people are infected. So let me show you who's infected, and I'm gonna shape them in black. Okay, so these guys are infected. Okay, so some people, unfortunately, have gotten infected. It's not a big deal. Hopefully they will recover, and so on and so forth. Okay. So in this particular example, I have 1, 2, 3, 4, 5, 6 people who are infected. Okay, now, I'm going to tell you how this disease spreads. That's called building a model. Okay, so model. Okay, how does the disease spread? Okay, so we know that some people are infected. Okay, and unfortunately that's not the end of the story. The disease is going to spread, and let us say that if 2 of your neighbors are infected, then you will get infected. So the model is 1, people are squares on a grid, and 2, if 2 of your neighbors, remember your neighbors are north, south, east, or west, if 2 neighbors are infected, then you get infected. Okay, it's a very simple model. Okay. And lots of viruses spread in this way. Okay. Now you might not agree with me about this model. Okay. It may not be that people live on a grid. And it may not be that specifically 2 neighbors need to be infected to infect you. Maybe just 1 neighbor needs to be infected. Maybe 3 people around you need to be infected. Okay, so those are details of the model. Okay, and let's not focus on them. Those details should be the sort of the job of the expert in virus spreading. Okay, it's not really the job of the discrete math guy. So we've come up with a reasonably simple model. Okay, and some people are infected. Okay. And if modeling is not our job as discrete mathematicians, then what is our job? What our job is to take a model or come up with a simple model and then ask questions, ask interesting questions. Okay, so ask interesting questions. Okay, so let's say first question, who gets infected? Certainly, the virus pops, a flu pops up every year usually. COVID has popped up. We've had swine flu, we've had, Ebola, we've had MERS, and so on and so forth. Okay, and an important question is, okay, so we know who got infected. Now, who started being infected, and now who else is going to get infected? Okay, so question number 1. Let's see if we can answer it. Well, it turns out that in this simple case we can answer it, but to answer it in more complex models and in general, that's where discrete math comes in. Okay, but let's answer it here. And I'll show you some interesting things. Okay, so, you know, does this guy get infected? Well, let's look. This guy has 3 neighbors, none of which are infected. What about this guy? This guy doesn't get infected. He has 4 neighbors, but only 1 is infected. Remember the model? The model says 2 have to be infected. Okay. What about this guy? Yes, look. This guy has 2 infected neighbors, so he's going to get infected. Okay, this guy, 2 infected neighbors, he's going to get infected. Okay, this guy, 2 infected neighbors, he's going to get infected. Interesting. Okay, so even though the disease only started with 6 people, now it's spread to 3 more. Is that the end of the story? No, because, you know, now that we've got, you know, in addition to the initial black infections, now we've got some new red infections. Now those red infections, together with the already existing black infections, can infect more people. And in fact, this can continue. So let's look now. Okay, it goes step by step. Okay, let's look at what happens next. Okay, this guy, yes, 2 neighbors infected. Okay, this guy infected. Will now get infected because these 2 are infected. What about this guy? These 2 are infected. Infected. This guy gets infected now. This guy gets infected. This guy gets infected. Okay, pause the video. I challenge you. Before I complete this infection, try to figure out who ultimately gets infected. Okay, so let me go. Unpause. In case you pause the video, here I go. Okay, so this guy gets infected. This guy gets now infected. Okay, and it looks like we've hit a barrier of no infections. But wait, now look at this guy. Okay, 2 neighbors infected. So this guy gets infected. But that's going to infect this guy now, and this guy, and this guy, and this guy. Wow. Okay. And is everyone going to get infected? This red infection is spreading just like a virus spreads through a population. Is everyone going to get infected? Let's see. Well, now, you know, this guy has 2 neighbors infected. Okay, so infected, 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 nope, wrong. This guy gets infected. So now it looks like maybe we've come to the end. Because look, a barrier of no infections. But look at this guy. Oh, 2 neighbors are infected. So the infection continues to spread, and now we're getting worried. The whole population is going to get infected. Okay, but look, this guy gets infected. 2 neighbors, this guy. 2 neighbors, this guy. 2 neighbors, this guy. You get the picture. Okay, this guy gets infected. This guy. Now this guy. And now we've hit another barrier of But this time, if you look at any of these uninfected people, you will observe that none of them have 2 neighbors who are infected. So by playing around with this model, okay, we have learned something very interesting. That, okay, we've got a reasonable model of how infection spreads, and this thing has spreaded and spreaded and spreaded and spreaded, and at some point, okay, the thing has petered out. Okay, of its own accord. We didn't have to do, you know, injections or this or that or vaccines. It's just petered out of its own accord. Okay, and this is what, you know, today, if you listen to the news, is something that's called herd immunity. There's not enough, infection around the uninfected people to infect them. Okay, so in some sense the herd has become immune. So this is an interesting example of where it's possible that, you know, a bunch of people got infected, 6 out of 49, roughly 11%. Okay, so a bunch of people got infected, but they didn't manage to infect the whole population. Not everyone got infected. Yay! Okay? I mean, not so yay, because look at how many people got infected, but still at least. Okay, so who gets infected? Okay, by playing around, we've come up with something interesting. Okay, now, that playing around, I call tinkering. Okay, when I first showed you the model and when I first showed you the 6 infections, you might look at this and say, okay, interesting, and okay, yeah, obviously everyone's going to get infected, but, you know, until you play around with the model, okay, you don't know. So you've got to play around with the model, become familiar with what's going on so that you can start making interesting conclusions that now the public health guy might find useful, and you might say, okay, you know what? Not everyone's going to get infected. Okay. Another interesting question. Okay, now that we have played around with the model, we might say, well, you know, clearly 6 people is not enough. But maybe it's just because of the way in which I arranged the initial 6 infections. Okay, question. Is there a way to arrange 6 initial infections so that everyone gets infected? Okay, now that may not be obvious, so now tinkering will be essential. Play around, see if it can be done. Okay, I'll tell you it cannot be done. Okay, so then we might ask, well, if 6 is not enough to infect the whole population, how many is enough? Okay, what's the minimum? What's the minimum initial infections to infect everyone ultimately? Okay, you can see this is a very interesting question to a public health person. You know, 6 is not enough. So if only 6 infections came into this population, in some sense you're safe. Not everyone gets infected. Okay, but how many need to come into this population and boom, it's possible to infect everyone? Well, it turns out, okay, that if you figure it out, you'll find that the number is 7. You can place one more infected person and infect everyone. Okay? But 6 won't do. It's not trivial to prove that 6 won't do. So you might try to think, how can I convince you that 6 won't do? Okay. Okay. And lastly, I'll just mention another interesting thing. When we started with the initial infections, we might have asked, supposing I could immunize some people. Let's say I could immunize 3 people. Okay? And I want to stop the spread as much as possible. Who should I immunize? Okay? Maybe I should immunize this guy and that guy. That would be 2 infections. Immunize, immunize, immunize. Okay? Now you can imagine what would happen. So play through this game and see that if I immunize these 3 people, okay, actually the infection won't spread at all. Okay? So that's interesting. 3 immunizations suffice. What about 2? Who should I immunize if I had 2? So, question. Who should you immunize to minimize spread? Should you immunize randomly? Should you target your immunizations? Very interesting question. Answering these questions, discrete math. You can see that these are all very relevant questions today. Okay. By the way, who should you immunize? If you're thinking about this, you're obviously not a politician, because I'm thinking about how to immunize people in order to minimize spread. But actually what happens in reality is the most powerful people, the most important people have to be immunized, even if immunizing someone else might have minimized spread. This is the real world. That's the real world. Okay. Next application. Speed dating. Okay. So, your daytime job is a Fox student, but in the night you run a speed dating club. Okay, so let's see what that club looks like. So we're going to build a model of your club. Wow, look at the speed at which I erase. Okay, so 16 people come. So you have 4 tables. Okay, so let me shade these tables. And if 16 people come to your club, so you have space for 16 people. If 16 people come, it means that 4 people sit at a table. So you have A, B, C, D. These are the names. I'm just labeling them. E, F, G, H, I, J, K, L, M, N, O, P. So 16 people came to your speed dating club. Okay, and let's imagine that they take seats. Okay. And you know, for reasons that will become clear later, let's call this round 1 of speed dating. Okay. Now, what we will, now obviously people, when they speed date, they like to meet people and then see if they get along, and then shall we, you know, go on a second date and a third date and get married and so on and so forth. Okay. So what we will say is that in this scenario, A, who is group speed dating with B, C, and D, A meets B, C, and D. So A meets B, C, D. Similarly, B meets C, D, and A. And C meets D, A, and B, and D meets A, B, and C. Okay, so A has met these 3 people. Okay, and that's good. So that's 15 minutes of speed dating, and then when this round is done, you know, they all get up and move around. Okay, but you, the speed date club owner, gets to decide how people move around. In other words, you get to schedule the rounds. Okay, so question, in the next round, who should sit where? Okay, well, that depends. So that's the model. That depends. It depends on what you're trying to accomplish. Okay, so let us say that for your club to be profitable, you need to make people happy, and people are going to get happy if they meet as many people as possible. So you'd like, in the next round, let's say, all the people to meet as many people as possible. Okay, and since you have an hour, and each round is 15 minutes of group speed dating, they chat and they figure out, you know, whether they like each other or not, and then they get up and move to the next round. So you've got round 1, round 2, round 3, and round 4. So you get to figure out who sits at what table in each round. You want people to meet as many people as possible. That's the task. It's a discrete math task. It might not look like one, but it's a discrete math task. So for example, question, is it possible? Is it possible for A to meet, you know, all 15 people? All 15 other people? Question mark. So can you carefully construct the 4 rounds so that A meets all 15 other people? So I'm not going to tell you the answer. I'm just going to tell you that, you know, here's the model, speed dating club. There are lots of interesting questions that we might ask, like, you know, what if I want to maximize the number of people A meets? How do I do it? What if I want to maximize the number of people on average that someone met? So A meets 8, B meets 10, D meets 11, and so on and so forth. And I take how many people each person met and average it. So, you know, depending on what's the goal, you know, how do you do it? How do you schedule the rounds? Scheduling rounds is a very hard discrete math problem. Okay. But we can solve it. And we need to solve it if you want to efficiently speed date. Okay, online advertising. Okay, this is related to another thing, which is a very important discrete math topic that's called a graph, but forget about the name for the moment. I'll just imagine that, you know, we have 6 friends. You know, in the previous example, we had 16 friends. Let's drop down to 6. So you have A, you have B, you have C, you have D, you have E, and you have F. So you have 6 friends. Okay, so we're talking about online advertising. Well, when you talk about advertising, you mean advertising to people. So imagine these are the people. Okay, now, okay, what's interesting is that, you know, some of these people are friends with some other people, and some people are not friends, let's say enemies, or they don't like each other. Okay, so let me show you who's friends with who by drawing a line between 2 people if they're friends. So boom, 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 boom. So AC are friends, AD are friends, CD are friends, and so on. Okay, so you've got a bunch of people who are friends with each other, and you've got pairs of people who are not friends with each other. Okay, now this is interesting. You might recognize, for example, you know, this group of 3 people, they're all mutual friends, and you might have called that a friendship clique or a social clique. And that's actually what we call it in computer science as well, in discrete math. Okay. Here's another social clique. Okay, 2 social cliques. Okay, and F looks like a loner. Well, you know, what can I say? F is a loner. Okay, kind of like me. Okay, So this is what we call a social network. Now, you know, you are an advertiser and you have one iPhone. Which you can give away for free. That's your mechanism for advertising. Who should you give it to? Okay, so now it depends. Depends on what's your goal. And typical goal of an advertiser is to maximize adoption. Okay, maximize the spread of usage. Okay, so you know, if you look at this graph intuitively, you might think, well, you know, let's try to make a model. A model could go something like this. You know, if you are in a clique of friends, let's say A, you know, that means you probably, you know, once a week you have dinner together, your friends. Okay, so if I give A the iPhone, my very precious free iPhone, I give it to A. Well, when A, C, and D go out for dinner together because they're a clique of friends, okay, then A, you know, gets out his iPhone to, you know, like browse the web, and then D and C look at, oh, what is that? Oh, that's an iPhone. Oh, I gotta get an iPhone. Okay, so you can think that if I give it to A, since they're a clique of friends, well, C and D will see it and then buy it. So I've managed to spread to 2. Can we do better? Okay, and looking at this graph, you might think, yeah, you know, look, you can instead give it to D. Okay, why? Because D is kind of in many social cliques, many social communities. On Monday, A, C, and D go out for dinner. D pulls out the iPhone to, you know, show off that he can check out his social media and, you know, go to the Fox webpage and stuff like that. And then A and C say, wow, you can go to the Fox webpage? I need to get an iPhone. So A and C buy the iPhone. Okay? And then on Tuesday, D goes for dinner with B and E because they're also a social clique. And then same process, B and E buy the iPhone. Okay, F, we can't reach F. Okay, too bad. Okay, so it's possible to do way better than giving the iPhone to A. Give it to D. Okay. Now, in this little baby social network, we can look at it and kind of maybe think, yeah, D is the best. But how do you do online social advertising to a social network like Facebook with a, you know, with a billion people and complex relationships? Okay, that's a discrete math problem. You know, you need to formulate it, and you need to figure out, okay, so who are the important people in the large social communities? Those are the people to advertise to. Well, what does important person mean? How do we find them? How do we make sure they're in large social communities? Okay, social communities sometimes could be called cliques. Okay, these are all discrete math problems. Okay. Once you give me the representation of friends like that and tell me what you want to do, you want to find the person who's the most important in the largest community, discrete math problem. Okay, so that's just to show you that a dizzying array of applications to which, if you want to answer fundamental questions, you need to be well versed in discrete math. Okay, now let me get a little bit more abstract and talk about, you know, the kinds of things that we like to do in computing. Okay, so